It is my pleasure to introduce today's speaker, Akbar Rafiey from Department of Computer Science. His research interests are algorithms, theoretical computer science, and computational biology. Today, he will talk about submodular functions. Here you go, Akbar.
Yeah, thank you. So, the focus is on the submodular function maximization. And also, I will be talking about the privacy aspects of the problem, and then we'll introduce some notion of privacy here. I'm not introducing, just basically talk about that. This is based on joint work with Yuichi Yoshida from NII, National Institute of Informatics. All right, let me, okay. Why didn't go to the next one? Yeah. Oh, yeah. Let me start with the problem definition and what is the problem from a very high level point of view. So let's say we have a sensitive data set. Well, it can be, so examples are like medical data or web search data, social networks or salary. And then there are some analysts who wants to do a statistical analysis of the data, okay? The analyst asks some queries about the data, and our purpose and our goal here is to answer to the queries while we preserve the privacy of data set. Okay, so this is like the general overview of the scheme of the work that we want to do here. All right, and so what do we want to achieve at the end of the day is that we want to return correct answers to the queries that are asked from analysts. And we want to answer those queries using an algorithm which is efficient, meaning that we can run it on big data sets. And then third, we want to preserve the privacy when we are dealing with sensitive data sets. Okay. And what we get in this paper, we consider a set of queries, set function queries, namely submodular set functions. And we present an algorithm for submodular maximization, and we prove the algorithm is efficient, it preserves the privacy, and it returns a good solution. In the second part, we consider a generalization of submodular functions, namely k-submodular functions. So this generalization allows us to capture more problems. And for this setting, we present an algorithm, and then we prove the algorithm is efficient and preserves the privacy and returns a good solution at the end of the day. All right, so well, I have been mentioning privacy of the data set. Let me just introduce the notion of differential privacy, which is a notion for privacy of individuals in the data set. So first, let me start with an intuitive introduction to this differential privacy. So let's say we have a data set, and then there is an analyst, let's say, for example, health insurance company, and the analyst asks the following simple query: how many people have diabetes in your data set? Then we do some computation, we'll count the number of people who have diabetes, and we output 100. Then we update the data set and we remove the record of individual X. Okay. Now the analyst asks the same question: how many people have diabetes? We do computation and say 99. So providing these two outputs, 100 and 99, the analyst knows that the individual X in the data set has diabetes. So by answering these queries, we have compromised the privacy of that individual. But instead, if we add some noise to our response, to our computation, and in the first case, if we say 100 people plus minus some epsilon have diabetes, and also in the second case, when we don't have the record of individual X, we also answer that there are 100 plus minus epsilon people who have diabetes in the data set. then there is less chance for the analyst to figure out if the individual X has diabetes or not. Okay, so in some sense, we have protected the privacy of that individual up to some extent. All right. So basically, from intuitively speaking, the point of differential privacy is that if we have two data sets which are almost the same, they differ only in one record, and we do some computation on those two data sets, we expect the output to be almost the same. So any one individual's data should not significantly change the outcome. Okay. Even if I want to put it in more formal and mathematical way, we have the following definition. Let epsilon and delta be positive reals. We say a randomized computation. I emphasize on the randomized part of the computation. So here we only talk about randomized computation. We say the randomized computation N is epsilon delta differentially private if for any two neighboring data sets, D and D prime, and when I say neighboring data set, I mean two data sets where they differ only by one record. And for any set of outcomes, the probability that the computation on data set D outputs something in S is almost the same as the probability that the computation M on data set D prime outputs something in S. So as you see in the definition, the difference, okay, let me turn on my pointer. So the probability are almost the same, up to some multiplicative error, e to the epsilon, and some additive error, delta. So through this talk, the setting that we consider delta is 0, but this is the general definition. Okay, so far I have been talking about like simple queries, counting queries, how many people have diabetes, but the queries can be more complex and more sophisticated. For instance, here through this talk, we consider set function query. So let's say we have a data set of 10 individuals, and each individual has some features, for instance, gender, diabetes, asthma, and then we have a classification of those individuals. They are either in class C1 or class C2, okay? Then according to those features, we can define a set function which help us to do this classification, right? So this set function with respect to this data set for any subset of features returns a value, assign a value to any subset of these features. For instance, if we have male and diabetes, then the value of those two features is 5. If we have asthma, the value is 7. And this value is with respect to how informative these features are with respect to the classification, okay? Now the query is, what are k most informative features? So what are k most informative features for these classifications of these individuals, okay? Now the task is answering to this type of queries while we preserve the privacy of individuals. So the set functions that we consider here are submodular functions. These are a class of set functions which are very popular, both in computer science and math and machine learning community. And they have nice properties, makes optimization over them simpler. So let me start with the intuitive definition of the submodular function. If I want to put it in words, the marginal contribution of any element E to the value of function diminishes as the input set S increases. Okay, what does it mean? Let's say you have $10 and I give you $10. Then the marginal contribution of my $10 to your money is a lot. Basically, I have doubled your money. But if you have $10,000 and I give you $10, then the marginal contribution of the $10 to your money is very slim. It basically diminishes as your money increases. Right? So it's basically the intuitive definition of submodular function. And then mathematically speaking, submodular functions are set functions where they satisfy the following property. For all subsets A and B, where A is a subset of B, and all elements E, which are outside of B. The marginal contribution of adding the marginal contribution of adding E to A is more than the marginal contribution of adding E to B. This is basically the diminishing gain property. All right. So far we have some understanding of differential privacy. We have some understanding of submodular functions. Now the problem is, so for instance, in the feature selection example, we were looking at sets of size at most k. We had sort of a constraint on the sets that we are looking for. So we consider general framework where we want to optimize, we want to maximize the submodular function under a matroid constraint. And matroid is a set of, is a pair with the ground set E and a collection of subsets with the following properties. The empty set is there, and if a set is inside the matroid, any subset of that is in the matroid, and it has the augmentation property. Okay. We don't need to know the definition of matroid for the purpose of this talk. I just want to say that, so the purpose here is, the objective here is to find a set inside the matroid, which maximizes the submodular function f, and we want to preserve the privacy. Okay. So as I said, the submodular functions are very popular, and there are so many problems which can be expressed in the framework of submodular functions. For instance, feature selection or influence maximization. Influence maximization, let's say you have a social network with some users, and each user has some effect on the other users, and then you want to select a set of users such that you maximize the influence in your entire network, right? Another example is maximum coverage, where we have a bipartite graph, and we want to select some vertices from one part, such that the neighborhood is maximized in the other part, okay? And other examples include data summarization, image summarization, document summarization, and so on. Okay. So a toy example that I borrow here from welfare maximization. Let's say we have a set of resources, M resources, R1 to Rm, and then we have N agents, agent 1, agent 2, up to agent N. And each agent has an interest over these resources. And that interest is expressed via a submodular function. And these are private information about this agent. Okay, so each agent has a private interest over these resources. And what is the objective? The objective is to find a set of these resources, a subset of these resources, which is in the matroid, whatever the matroid is, and such that we maximize the happiness of everybody, the happiness of all these agents, right? Well, and this is like, this problem is called like welfare maximization, okay? So what do we do? What are our contributions? For the private setting, there was, in non-private setting, there is 1 minus 1 over E approximation ratio. And in private setting, the previous result due to Mitrovic et al. Is half of optimal minus some additive error. We improved this approximation ratio to 1 minus 1 over E times the optimal minus some additive error, which is worse than the additive error of Mitrovic et al. And our privacy guarantee is epsilon times rank of matroid square, while the privacy in the previous result was epsilon times rank of matroid. And note that this 1 minus 1 over E approximation ratio is the best possible one can achieve. So later in the talk, I will explain about this additive error, and then we will go in more detail and explain the parameters in the additive error, okay? Then we consider generalization of submodular functions. As I said, k-submodular functions. Now here, instead of having sets, we have tuples of sets. Okay, we have k tuples of sets, S1 to Sk, and T1 to Tk, and then we have the submodular property. Don't bother about the definition here. It's like, I know it's a lot to digest in a talk. So what it means, this k submodular means that for every orthen of this k orthen, the submodular property is satisfied. Okay. And of course, when k is 1, then we have submodular function. Okay. So this framework k-submodularity led us to express more problems, and it is more expressive. For instance, consider influence maximization. As I said, we have a network, and each person has some influence on the other people in the network. And now here we have k topics, and we want to give these k topics to some people in the network such that we maximize the influence of the number of we want to maximize the number of influenced people in the network. Okay. All right. So a toy example for submodular for k-submodular functions. Let's say we have a set of add slots, V1 to Vm, and we have a set of users, U1 to Un. And then we have an influence graph, G1, which is corresponding to the ad agency 1. So it means that if the ad agency number 1 put an ad on slot V1, then it's gonna influence user 1 and user 3. Okay. And then for ad agency number 2, we have a different graph, the same set of users, the same set of added slots, but the edges are different. And the edges are specified by this ad agency number 2. And so on. And the same for ad agency number k. And what is the object? So the edges that we have here are private information about users, right? So each ad agency has some private information about these users. And the objective here is to allocate at most B ad slots to the ad agencies such that we maximize number of influenced users. This is an example of a k-submodular function, maximization, when we care about the privacy. So what we do, we provide the first differentially private algorithm for this setting, and our approximation ratio is half of optimal in worst case, plus some additive error, and the privacy guarantee is epsilon times rank of the matroid. And this half approximation ratio is best possible one can do. Okay. So far I have given an overview of this differential privacy, the notion of differential privacy, and then submodular functions and the setting that we consider here. So that was like sort of the first part of my talk. Now in the second part is going to be a slightly more technical with more definitions, and I will be talking about some tools for designing differentially private algorithms, and then how to use these tools to do an optimization, submodular optimization. All right. Let me remind you the definition of differential privacy. So we want a randomized computation that it satisfies the following, right? For any two neighboring data sets D and D prime. And this randomized computation that we have, it has to inject some noise in the computation, right? But the amount of noise that we inject depends on how sensitive our data set are, right? So basically, let's say we want to optimize a function over this data set. If the function that we are interested in is very sensitive to small changes in the data set, then the amount of noise that we have to inject in our computation should be a lot. But if the function that we are working with has low sensitivity with respect to the small changes in the data set, then the amount of noise that our computation has to inject is very small. So the amount of noise that we have in our computation, it relates to the sensitivity of the function that we are working with, okay? So here is the definition of sensitivity, which is basically what I just told you. And we call the function, if the function has sensitivity delta, we call it delta sensitive, okay? Now, let me talk about exponential mechanism, a very simple mechanism and very elegant mechanism to design differentially private algorithms. So let epsilon and delta be greater than 0. And we have a set of candidate R, and then over those set of candidates, we have a quality function. So some of those candidates are good for whatever reason, some of them are not good, okay? Then this exponential mechanism choose a candidate from the set of candidates with the following probability. What is the probability? Is epsilon divided by the sensitivity of Q times the quality of that candidate, right? So as you see, the probability is proportional to the sensitivity, the quality, and the privacy that we are looking for, okay? This is a very simple mechanism, but very powerful. And in 2007, McSherry and Tolmer proved that this mechanism is epsilon differentially private. And another good thing about this mechanism is that with high probability, it outputs something which has a good quality. So with probability at least 1 minus beta, we output something that has quality which has this distance from the optimal quality, right? So this is the distance that we have from the optimal quality candidate, from the quality of the optimal candidate, okay? So this exponential mechanism has two properties. First of all, it's epsilon differentially private. Second, with high probability, it outputs a good candidate, whatever good means, okay? Now let me elaborate more on matroids and matroid polytopes. So we want to optimize the problem over matroids. Then I will be talking about matroid polytopes. Then the optimization over matroid polytopes is simpler. So just to remind you what was the matroid, an example for matroid is uniform matroid, where I, the set of independent set in the matroid, is basically all the subset of size at most k. This is called like a cardinality constraint or uniform matroid. And other examples are like linear matroid of matrices or graphical matroids and so on. So what's the matroid polytope? we can represent any subset in the matroid using a 0-1 representation. So using a characteristic vector. So if we take the convex hull of those characteristic vectors, it's gonna be the matroid polytope, right? So you can define it in other equivalent ways, which in terms of rank of the sets, which I'm gonna skip here. So an example for a matroid is the following, where we have these base sets in the matroid: 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and then one characteristic vector for these sets is basically 1, 1, 0, 0 for the first one, 1, 0, 1, 0 for the second one, and so on. So now taking convex hull of these guys is going to give us the following matroid, as you see in the picture. Okay. Now, while I was talking about exponential mechanism, the exponential mechanism was applicable on the discrete set of objects. Right? We had a set of candidates, and between them, we choose one. But now when we work with matroid polytopes, it's a continuous space. So I want to sort of discretize that matroid polytope and have a covering of that matroid. So what is the covering? Let's K be a set in R to the E. And then for any positive row, set C is a covering, is a row covering of K if for any X in that set, there exists Y in the covering such that the distance between X and Y is at most row. Okay, so basically I have this matroid and then I put the small balls inside this matroid, right? And the center of those small balls are going to be my covering. Okay, luckily due to results by Yoshida in 2019, if we have a matroid, then we can cover it with this many, with at most this many, with at most this many points in the covering, right? So it's E to the inverse quadratic of the epsilon. Okay. And the ratio of the row for the covering is basically epsilon times B, whatever B is. Okay. So such a discretization is useful for us when we want to use the exponential mechanics. Okay. So let's relax. So far, everything has been like the play between discretization and continuous stuff. Let's relax things. So let me overview what we want to optimize here. We are looking for sets in the matroid such that they maximize the submodular functions, okay? Or equivalently, we are looking for 0, 1 vectors of length E that maximize f of x, okay? So now I can relax this condition and work with 0, 1 with real vectors of length E with entries between 0 and 1. And then now instead of f of x, I need an extension of f. And as soon as I have the extension for f, I can reformulate the problem as finding a vector in the matroid polytope that maximizes this extension. And this problem is known to be polynomial time solvable, right? So what is the extension of f that I am considering here is the multilinear extension. This, you don't need to know the definition of multilinear extension for the purpose of this talk, but there is a nice probabilistic interpretation of this multilinear extension. So the point of this multilinear extension is that it has nice properties which help us to optimize over the matroid polytope, right? And what are those properties? So for like integral solutions, it is basically the same as the original function itself. And if we have a fractional solution x star to this extension in the matroid polytope, then we can obtain an integer solution by swap rounding techniques introduced in 2010, right? And by using this technique, the swap rounding technique, we don't lose any value in the function. So f of z, the integral solution, is greater than a small f of x, okay? So this multilinear extension also preserves some properties of monotone submodular functions. Namely, it preserves monotonicity and concavity along any positive direction. This helps us to optimize the multilinear extension over matroid polytope. Okay, now we are at the place where I can explain the our algorithm, which we call a differentially private continuous greedy algorithm. Yeah, so first we have this matroid polytope. Then we discretize this matroid polytope and cover it with C row points. And we start with the vector, which is all zeros. And the algorithm has T rounds. And at each round, we try to move in a direction inside the matroid polytope. And that direction is supposed to improve the quality of the function, okay? But how we choose that direction is coming from exponential mechanics. So a quality of a point Y in the covering is basically how much it improves the function at the current point. So then between the points, between all possible directions, we choose one using the exponential mechanism, right? And then we set xt plus 1 to be xt plus alpha. So we take a step in the direction y, and the length of the step that we are taking is alpha. And alpha is the learning rate, right? And we return x of t after t iterations, right? So what is the utility of our algorithm? So we can prove that if the function is delta sensitive, the utility of the algorithm, the output, the quality of the output is 1 minus 1 over e times the optimal one minus some additive error. And when we are working with low sensitivity regime, then this additive error is very small, right? And this rho is coming from the covering. So if it, yeah. So some proof ideas. As I said, the exponential mechanism with high probability gives us a direction which is good enough. And then we collect all these improvements over the course of the algorithm, and at the end say that if we add up all these small improvements, then we end up at a good point. Okay. And the privacy, it has epsilon times rank of matrices square privacy guarantee. So recall that the exponential mechanism was epsilon differentially private, and we use this exponential mechanism for t rounds, or where we can set t to be rank of matrix. And then if the function, the original function is delta sensitive, its multilinear extension is delta times Rm sensitive. So putting everything together, we end up with the privacy E times Rm squared. Okay. And recall that the algorithm at the end returns a fractional solution, but as I said, we can turn this fractional solution to an integral solution using swap rounding technique, which is private, which is a private technique. Okay. Now, now the question that we ask here is the following: do we need to consider the entire covering when we want to select a direction, or is it enough to work with the subset of those points? So it turns out that we can work with the subset of those points in the covering using a sampling technique and work with those subsets. As long as that subset of the points that I'm selecting from the covering is reasonably large, then I can focus on that subset instead of looking at the entire cover, right? So the algorithm overview, an overview for the algorithm is as follows. We partition the covering into some layers such that points in the layer, they have almost the same improvement if I take the direction of those points, okay? And then instead of choosing a point in the covering, we choose a layer. And then from that chosen layer, we choose a random direction, right? So the whole point here is that instead of looking at all the points in the covering, I collect them, put them inside beam, and the directions inside beam, each beam, they have almost the same improvement. And then I select a beam, and from that beam, uniformly at random, I select the direction. Okay. So how do I define a layer or beam? It depends on the quality of points. So they almost have the same quality. Their quality is between 1 plus mu to the power of I minus 1 to 1 plus mu to the power of I. And then for each layer, we define this random variable zi tilde, which is basically the size of that layer times the quality. And z tilde is the summation over all these k layers, okay? So by Hoffending qualities, if I sample sufficiently large number of points from the covering, then we can estimate this ratio. We can guess what is the what is the number of points in each layer. Okay. So the algorithm in more detail. Again, we start with 0, vector of all zeros. Then it has t iteration, and each iteration we sample some points from the covering. Then partition them into layers and estimate what is the size of each layer. Then depending on the quality of layers, with some probability, we choose a layer, and then from that layer, we choose a point, or basically a direction. Then as before, we take that direction and move towards that direction. Okay. So the utility analysis is slightly different because we have put mask over this exponential mechanism, right? And then we have to prove an analogous version of this exponential mechanism. And then at the end of the day, we can prove that we still get 1 minus 1 over E approximation to the optimal. But as you see, the additive error is worse, right? In terms of privacy, the privacy analysis is almost the same, but there are some difficulties that we have to overcome. And this includes, like, if we have two neighboring data sets, we want to show that the number of layers is almost the same, and a point lies almost into the same layer, or in respect to the two data sets. Okay. Now let me talk about this k-submodular functions, which means like orthent submodularity for every orthent. For any, let me check how much time I have. For any k tuple of subsets, S1 to Sk, we can associate a vector S, which is from 0, 1 to k to the power of E. And if we have this vector S, then Si is defined to be as follows. Don't bother about the definition. Then we have the concept of monotonicity for every orthent. And then we have the definition of marginal gain if we add an element to the IS set. And then the monotonicity means that the marginal gain is always positive. And as I said, we have orthent submodularity. Okay. Let's see some useful lemmas. So what we want to do, we are looking for a vector in k plus 1 to the E that maximizes the submodular function, subject to the union of sets that I am considering is inside a matrix. Okay. The first lemma says that any optimal solution has Rm elements in it. Okay. The second lemma says if you don't have Rm elements in your current set, then there is always something that you can add and improve the quality of the function. So this suggests a simple algorithm. So the algorithm runs in Rm iteration, and at each iteration we choose an element with probability proportional to its marginal gain using the exponential mechanism. And by the second lemma here, we can add that element to the current set and improve the function. Okay, so the utility of the algorithm is we can prove that with high probability, the simple algorithm returns a point which has quality at least half of the optimal minus some additive error. And then in terms of privacy, it's again simple because we have exponential mechanism, which is epsilon differentially private. And then we use that mechanism for Rm rounds. So the privacy is going to be epsilon times Rm. Okay. Now, once again, we don't need to look at all the possible elements. Then we can use this sampling techniques to improve the time complexity of the algorithm. So the idea is we use a sampling technique and sample sufficiently large subset of elements and work with that subset. Okay, let me give you an overview of the algorithm. Once again, we have Rm iterations, and at each iteration, we sample a random subset of this size, okay? And then we choose an element from that random subset with probability proportional to its quality, to the marginal gain, using the exponential mechanism. And then we add that element to the set and go on. So this algorithm may fail with some probability. And the reason it may fail is that this random subset R that we have here may not contain any element such that we can add that element to the current set, okay? If this even happened, then the algorithm fails, but we prove that the probability that the algorithm fails is very small, gamma. So with probability at least 1 minus gamma, the algorithm returns point, which is half of the optimal minus some additive error. Observe that this factor gamma is in the additive error right now. And the proof sketch is basically as before. The only difference is that we have to be careful about the failure probability, right? Then one can prove that if we use this sampling techniques, the number of function evaluation is going to be k times the size of ground set times some logarithmic factor, which is linear in the ground set, okay? And in terms of privacy analysis is identical to the previous case. We have exponential mechanism and we use this exponential mechanism for RM rounds, which is going to give us epsilon times RM differential privacy. Yeah, so this was what I had to say about privacy and submodular maximization. Please ask question if there is